Check, check, check. Check and check, check. My name is Chris, and I'm adjusting my mic level. Check, check, check. Anybody? Hey, everybody. Okay. Can you hear me? Check, check, check. My name is Chris, and I'm wearing a wrinkly shirt. Hear the white noise. What about now? Do you still hear the white noise now? I just turned off my little fan. So I know there's a 20-second delay, but I can't wait. You have to tell me now. Tell me now, darn it. Go ahead and send me text messages so I don't have to show the admin chat on the screen. Yeah, go ahead and send me a text so I can be sure that everything's okay. We'll start in a few minutes, so we usually start at noon, that sort of thing. This is my wrinkly shirt. The wrinklier the better. Pro tip is to use a darker colored shirt with a green screen. If you use lighter colored shirts, it doesn't tend to work quite as well. And we're going to talk a little bit about astronomy stuff today, and the overlap with data science, that sort of thing. So good. Okay. Yeah, the white noise must have been my little fan. I'm going to shut this door over here so the dryer sound doesn't come on screen. So, a second. Can't necessarily see the chat. Scott's watching the chat. Big thanks to Julie Butler for her session yesterday, which she's extremely knowledgeable about Excel in ways that I am not, so hats off to her. Six minutes. How's everybody doing? So we'll start in about 3 minutes. I'm going to stand up here and try to think of things to say for 3 minutes. So thanks for tuning in. Hope you're enjoying our data science series. This is the first time we've done data science training before. We've done a lot of physics training, done a tiny bit of astronomy training. And I'll tell you what this is in just a second. Yeah, I hope everybody's having a good summer. Maybe I'll close this so it doesn't pop up on the screen there. It seems like a good idea. Let's see, is it this? Is that? Yeah. Great. Alright, 2 more minutes, we'll get started. Alright, 1 minute left, we'll get started. So I'm going to start here. Alright, so 12 o'clock, lots to say. Glad to be here to do another live stream with you all on the STEMcoding high school data science curriculum, which we're still building. We're assembling the parachute as we fall from the sky, you know, riveting the plane as we glide through the air. And so I'm going to give you a couple things that some ideas, inspiration for high school data science today. I hope you enjoyed the stream yesterday where Julie Butler talked about data cleaning, or what some people call tidy data, which is an important part of data science. So the main thing I'm going to talk about today is an activity called the Night Sky Simulator, but I'm going to hop to a few different things before we get to that point. So as a reminder, STEMcoding super friend Kristen Hunter Thompson, she just recently started her own YouTube channel. So we really encourage you to check out her YouTube channel, which is all about data, not just high school data science, but also elementary and middle data literacy. And she's the GOAT, people. So she's been doing data science and data literacy since before it was cool, well before the 2019 Freakonomics episode that got the entire education sphere interested in data science. And so she is the person you should be listening to. I'm smart too, but I'm not quite as smart and as knowledgeable as Kristen Hunter-Thompson is in all these things. So I encourage you to check out her videos that she's worked so hard to put up there. Another high school data science thing you should know about is that there's a group called Data Science for Everyone, which is based out of the University of Chicago. If you are in the know about, if you've listened to the Freakonomics podcast, which got everybody interested in data science, the Freakonomics podcast is led by an economics professor at the University of Chicago. So it is not a coincidence that this group is also at the University of Chicago. But there has never previously been a K-12 data literacy, data science focused conference. All of the conferences up to now in which people talk about data science have been, part of larger math conferences, or there have been data science sessions at National Science Teachers Association meetings, that sort of thing, or at CSTA. This is the first dedicated data science conference. It's going to be in, I think, February 2025, and the abstract deadline is coming up, which is a good reminder for me so that we can submit our abstracts, so we can, because we're planning to go, we're planning to present. And I believe it's in Texas somewhere. So it's going to be in February. It's going to be cold, but they're smart people, and they're going to do it in Texas instead of Chicago. So please come to the epicenter of data science education next year. And if you can't submit an abstract, please just try to attend. All right, so those are the things to preface. So I'm going to go over some activities today, and the STEMcoding data science curriculum has a kind of a physical science theme to it. You've seen the air pressure data. The ecology data is sort of science data. It's not necessarily physical science, but that's still science data. And a fun part of physical science is astronomy and earth science and all those sorts of things. And so in the STEMcoding project, we've built a couple of astronomy activities. So like you can see, I think all these activities are on the YouTube channel. Maybe not these two. I guess we haven't had time to do video tutorials for these two. But these are the astronomy activities that we've developed. And these ones are not as much data science, but this one definitely is, and that's the one I'm going to talk about. So I'll talk about that one in just a second. And then, just as a reminder, earlier I introduced this thing, which I need to clean this up. This was for a college astronomy class that I made, that I taught many years ago. But the basic idea of it, you can easily take the ball and run with it, is that you challenge your students to use a spreadsheet to design a scale model of the solar system. And so you can ask each group to decide on how big of a model they're going to do. Are they going to fill the classroom with the solar system? Are they going to fill a basketball court with the solar system? Are they going to fill a soccer field with the solar system? Are they going to fill, the entire campus with the solar system? They might not actually build it, although you could. But the idea is you want to put in the real distances from these planets to the sun, and then you want to scale them to something that fits into those spaces. And so it's a good example, it's a good opportunity to use like a multiplier and to do it that way. So this is, if I was going to teach a high school data science class, I would use this as one of the first activities. And again, it connects with physical science, it connects with earth science, solar system, astronomy type stuff. So this is pretty simple. The Night Sky Simulator is not the simplest thing I've ever done, but this is a pretty good start if you're going to do more astronomy stuff. But it's your class, and so we're developing these activities, and you can pick and choose. Our goal is actually to build more than a year of high school data science content, so you can have a buffet of options to create your course and stitch it together. And if you want to use Google Sheets, that's fine. If you want to use Excel, that's fine. It's up to you. So all right, so that's that. I'm going to talk now about the night sky simulator activity, and let's see. So you can So you can get to that with this link. So which maybe Scott has already put that in the description of the YouTube thing. So you can start with this link, and we do have a nice video on the STEMcoding YouTube channel in which we go through the night sky simulator, and so there's part of me that feels like this is a little bit superfluous, but I just want to walk through it while we have your attention. And so if you click on this link, it will open a code, and the code looks like this. And I think I already modified this one. Maybe is that? I can't remember. So the code looks like this, and if you run the code, it looks a little bit like this. Now, these are random dots on the screen, and it looks a tiny bit like a night sky, but not really like a night sky, right? And so this does look a bit more convincing like a night sky, doesn't it? So, because when you look up at the night sky, some stars are super bright, some stars are pretty dim. The actual night sky, some stars are a little bit more blue, some stars are a little bit more red. We didn't quite get that far in this activity. But this is a fairly convincing night sky, whereas this is not as much. And so what's happening here is that we're generating the position of each star. So imagine that there's a cube here that has dimensions 500 by 500 by about 20. So it's thinner than it is wide, right? And then each star gets populated in that cube. So like this screen is really a cube that goes back 20 units, right? So that's the Z, right? And then this draw star, really it's drawing a little spot, but the idea is that the idea here is that each star has the same size, in other words, the same brightness, and whereas through a few steps we're going to change that. And so in the real night sky, stars have different brightnesses because some stars are closer to you than others, right? And so the first thing that you can do is you can say that each star is emitting the same amount of energy per second, but because some stars are closer to us and some are further away, that would affect the size of the dots on the screen. And so you can do that by something like this. So the brightness is equal to the luminosity divided by 4 pi d squared, right? And part of what I think is cool about this activity, and part of why I think you should consider it for your high school data science course, is that there's this big criticism that high school data science doesn't have enough polynomial algebra type stuff that prepares kids for, say, college algebra, right? So here's your college algebra, right? And so I can copy this into our program. I actually have to delete this, is the idea. And so that third thing here is the brightness, and that determines the size of the dot. It's a long story why we multiply by such a large number, but anyway, so when you do this, now you get something that looks a little bit more like a night sky. So these are kind of bright, and presumably these are bright because they're close to you, whereas these ones are a little bit smaller because these stars presumably are further away. We're assuming all the stars have the same luminosity. So we're assuming each star is basically like our sun, emitting the same amount of energy per second as our sun. It's just that some are closer and some are farther away. So that gives us a slightly more realistic looking night sky, but it still doesn't quite look right. Because if you go and you look up at the night sky, you see some stars that are very bright and some stars that are very dim, and we're getting a little bit of that dynamic range here, but not so much. So we needed to take another step, and this step is definitely based on It's in solid science. So here's what we're going to do is we're going to appreciate that there's a relationship between the mass of the star and how much light that it's emitting. It turns out that if your star is twice the mass of the sun, if you think deeply about the way that stars work, then you can conclude that if it's twice the mass of the sun, then 2 to the 4th power, what is that? So that's then it should be 16 times as luminous as the sun, right? So stars that are twice as massive as our sun are emitting energy 16 times more energy per second than our sun is, right? And that's going to make them brighter, for sure, right? So the relationship is that the luminosity, in terms of the units of the luminosity of our sun, is equal to the mass to the 4th power, where the mass is in the units of our sun as well, if that makes sense. So like this thing turns into that thing. So what we're going to do is we're going to randomly generate the masses, like that. So we're going to randomly choose the mass of a star. Each star has a different mass now, ranging from 0.25, the mass of the sun, to twice the mass of the sun. And then the luminosity is going to be, if you follow the directions here, the luminosity is now going to be like this. So m to the power of 4. There's 2 different ways to do that. So you could do this, because in JavaScript that's how you do the power. Another way to do it would have been to do, just to prove to you that it's possible, you can also do that. So that's m to the 4th power. It's whichever way you want to do it. I'm going to go back like that. All right. So now we are randomly choosing a mass for each star. We're generating 200 stars. Each one has a slightly different mass. Each one has a slightly different luminosity. And then that luminosity, combined with its distance to us, determines what the brightness is. So now when you do that, now you get an even larger range of the size of these things. So you get a wider range of brightnesses, essentially. And so now this actually does look quite a bit more convincingly like our night sky. And so that's fine, right? Maybe I should have said this earlier, but a central question that we're addressing with this exercise is that when you go up and you look at the night sky, when you see a bright star, like this, is it bright because it is especially luminous? Is it, when you see a bright star in the sky, is it bright primarily because of how much energy per second that it is emitting? Or is it bright because it just simply is very close to us, right? Which one of those two things? Maybe it's both of those things, right? Or is it one dominating the other, right? So because both the energy per second matters, but also the distance matters. So that's the fundamental question. And then another way of phrasing that question is that when you go up and you look at the night sky, is the closest star to us also the brightest star, right? Because if it's the distance that primarily determines this brightness, then the closest star is going to be the brightest one. But if instead the luminosity has a bigger effect, then this thing might be ridiculously bright, and it might be closer to us, it might be further away, right? But maybe it's just so darn luminous that that's the reason why it looks so bright in the night sky. So that's the basic data question that we're addressing in this activity. So we're not just making a nice picture, we're trying to answer an important question about nature. And what you can do is you can save, you can add some stuff to your code. So you want to save each value. So a good place to put it is right here. So we've generated a star, we've generated its brightness, its luminosity, its position, and we're going to save each individual value. But then when we've generated 200 stars at the very end of our program, and right before we close our program, we can add this extra thing to save it. By the way, a fun fact about this interface is that if your students like the stars that they generated, all they have to do is right-click and save the image as. That'll save a PNG file to their screen if they just want to save the image. So that's part of the fun of this activity. Maybe they want to save it and then draw lines through it, make constellations. I don't know what they want to do with it, but all right. So I've added that code. And it's those two changes, and now I'm going to run it again. It's going to generate 100. It's going to generate 200 stars. If you want to generate more stars than that, that's totally fine. Sometimes it's fun to generate more stars than that because you can see all these faint stars in the background. It just starts to look prettier and prettier. But what it's doing is that it saves a CSV file, which is a file we can easily open in a spreadsheet program. So I have already kind of opened this in here. So this is a file that I saved, and I opened up the stars.csv. This is for a different randomly generated data set. But now that we have this table, we can sort the table to try to figure out is the brightest star also the closest star. And so this z is the most important thing for the distance, right? Because we can see there's the x and then there's the y, right? But the z is what determines our brightness and the way that we're thinking about it. And so we care a lot about this column, and we care a lot about this column, not so much about the luminosity, not so much about the mass, not so much about the x and the y. But what you can do is you can highlight this whole thing, and the first thing I think that you want to do is you want to sort by the first column. So you're going to do data sort, and you can sort the sheet by column A, and I think you want to do Z to A. But so if I sort it by the brightness, there's one star that is quite a bit brighter than all the others here. Okay. If I still had the image saved, I could maybe try to figure it out. So there's one star that's brighter than all the other ones. These are almost as bright, but not quite. And then we can see that this star is at 2.2 distance. You can maybe think of this as parsecs if you want, I suppose. And so the next thing we can do is we can sort on this column C. Is this star also the closest star? Right, so I can do the same thing, and now instead of sorting the sheet, I can sort the range. I can use the advanced thing. And I don't want to sort by column A anymore, I want to sort by column D. So I'm going to sort by column D, and I think I want to go A to Z, and so I'm going to sort by column D. And what we find is that although the brightest star is very close to us, the closest star is actually not very bright at all. And so the closest star in this night sky that we've generated is actually not the brightest star. And that turns out to be true in real life. So if you look at so somewhere there's a list of, So these are all the lists of the closest star systems, and there's a nice little table. So like Alpha Centauri, for example, is our closest nearby. If we were going to send a spaceship out to the nearest star, we would send it to Alpha Centauri, which I believe has multiple stars in the system, which is why there's like 3 of these things, right? Because there are a lot of binary and triple star systems out there. The sun, not all solar systems are like ours, they just have the one star. So Alpha Centauri, although it is the closest star system in the sky, it is not the brightest. And if you dig into this long enough, this is magnitude, let's see, 11 star, something like that. So that's not a very bright star, basically. So that lines up with facts. Now when you do this, and when you analyze the data, you may find that in fact the brightest star is the closest star, and sometimes that does happen. It's a randomly generated data set. Sometimes that's going to happen. A thing that can make this exercise a little bit more realistic, which we talk about, is that if you go and it turns out in real life that just randomly selecting the mass of the star between 0.25 and 2 is not very realistic. Stars are actually much more likely to be low mass than high mass. So there are many more stars that are 0.25 and 0.5 solar masses than there are 2 solar mass stars. And so a thing that you can do is to address that is you can use this thing, which is built into the code, and that will make it so that there is more. So you can stick that into there, replace this. That's the only thing you need to change. And now, if you just visually, if you look at this night sky, you might be able to see the difference. So there tends to be more dim things here, and then you can analyze that data set. And in that data set, when I did it, I found that, so this is the data set that I have with that one. So these are the brightest stars, and they are pretty close to us, but if you sort it according to the distance, you sort it according to the distance, then there's actually 2 stars that are closer to us than the brightest star. I think in real life it's probably even more than that. So this is an interesting toy model for creating the night sky that has some good algebra in it, like as I've described, and it also has some good data analysis skills, some good spreadsheet skills in it. And so I'm quite proud of this activity, and please, even if you're not, if you feel like you're not as expert as astronomy as you'd like to be, please consider it for the data science course, because there are these, a lot of times in data, there are these relationships, and this is a pretty complicated data set that comes ultimately from this thing and from this thing. So in the whole scheme of things, this is not the most complicated data set you've ever seen. But it's interesting that there's these polynomial relationships that give rise to this rich phenomena. So that's the activity that I wanted to share with you today. It exists here. It also exists on our learning management system thing here. So on STEMcoding Heroku app, it's also there. So we had, if you're on the Discord, you know that there's a course you can join here, that if you want to fill these out here. This actually wasn't working very well until this morning, until I fixed it. So I did actually make that improvement. But that's what we have to share today, and we'd be happy to have your questions in the Discord and that sort of thing. So yeah, thanks for your attention, everybody.